So last session we stopped here and we were going through the structure of inception module. And this is called GoogLeNet when you stack multiple inception modules on top of each other. The idea was that they wanted to figure out whether they should use 1x1 convolution or 3x3 or 5x5 or max pooling or etc. And they said, why not use them all? That's a good idea, but there was a catch that they could make their network more efficient by first projecting into a low dimension using 1x1 convolutions. So 1x1 convolutions are good for changing the number of filters, basically changing the number of dimensions. Another name for it is called feature maps. So you're changing the number of feature maps. And basically you're going from a high dimension to a low dimension, then do your convolutions in low dimension, which is going to be more efficient. And then you concatenate them all channel-wise. So the entire architecture is going to look like this. The first few layers are going to be very similar to what we have seen before. Basically a 224 by 224 by 3 image, which is a tensor of red, green, blue, goes into the first convolution. The first convolution is 7x7, and it has a stride of 2. And because the stride is 2, your resolution is gonna become lower. So the resolution divides by 2. And then you're having 64 filters. And the depth is 1, and you have this many parameters and this many operations.
What does it mean by depth? Is depth just what you've shown on the right, like the model A all have depth 1, and in model B there's some depth 2 layers?
No, for the first one, it's just a convolution from before. So whenever you have a weighted layer, that's going to add 1 to your depth. And then usually you're concatenating multiple layers on top of each other.
Got it.
You can think of them as function compositions. So this is the first function. Takes as input an image and outputs a tensor of this size. Takes a tensor of 224 by 224 by 3 as an input and outputs this. But because this one has a bunch of weights and biases, we are going to count it as 1 layer. So it's adding 1 to your depth. Okay. Then you have max pooling. Max pooling is going to be done over 3x3 windows. It has a stride of 2. So you are dividing 112 by 2, it's going to give you 56. And max pooling is done channel-wise, so the number of channels don't change. And it doesn't add to the number of your layers. So it's not adding to the depth, because it's not parametrized. Okay. Then you use 2 convolutions, 3x3, stride of 1. Because the stride is 1, the resolution doesn't change, but they have different dimensions. One of them is doing a reduction. The other one is increasing the dimension. Then another max pooling. So you had 2 layers of convolution after the first max pooling, and then another max pooling layer. And because the stride is 2, the resolution goes down. So it's usually the trend in image classification. You want to summarize your image and make it lower resolution as you go deeper in your network, but then you want to add to the number of you want to increase the dimension of your channels. Are there any networks that add a learned weight to the max pooling? Seems like it's always a normal averaging. I've never seen any weights associated with max pooling. So no, it's just you take a window of 3 by 3, which are basically 9 numbers, and you report the maximum. And then you slide that window over your image. Does that answer your question, Sarush?
I think
Perfect.
adding weighting would just be the same thing as a convolution. You would take a neighborhood or a patch of the image and weight different pixels accordingly.
I think his question relates to, I think he has read something about activation functions having some parameters, making them parameterized. And that's why he's asking about that. But yes, convolutions are going to do the parameterization for us, and max pooling is just to make things locally invariant to translations. So it's going to be invariant to small translations of your image, up and down, when you do max pooling. Okay. So up until this point, it's the same as before, what other people were doing. But then here is where inception, the first inception module comes in, and that's of this form. The resolution is the same as before, and the output size is going to be after you concatenate everything. So what are you concatenating? You're concatenating a 64-dimensional 1x1 convolution. You're concatenating 128 3x3 convolutions. So these are the number of filters. So this one has 64 channels. This one has 128 filters. This one has 32 filters. And then there is a max pooling that has 32 dimensions. And if you add them up, you're going to get 256. But what are these numbers? 96, 16. These are these 1x1 convolutions that are first projecting into a low dimension, to a 96 dimension, for instance, and then you go to 128. This one projects into 16 dimensions and then 32. So is everything clear? How the inception module works? Any questions? The question is, how is this reducing the dimension? So what is a 1x1 convolution doing? It takes a pixel, and each pixel, for instance, here you have 28 by 28 pixels. Take one of those pixels. That pixel is going to have 256 dimensions. And then what 1x1 convolution does is just multiply that by a matrix to change the dimension from 256 to 96, for instance. So your matrix is going to be 256 by 96. And it's the same matrix for every pixel. So you do the same operation on every pixel. That's the 1x1 convolution. And the way you change dimensions is by matrices, matrix multiplication. And your matrices are of this size by 96.
If that's the case, then what is that highlighted 64 representing?
Which one? This one?
Correct.
This is for this first 1x1 convolution. The first one is a 1x1, and then you keep the 64 filters that you have. So it's exactly the same thing as I explained.
Okay.
This is the one-by-one convolution. So it's changing your dimension from 256 to 64. This is a one-by-one convolution that is changing 256 to 96. Okay.
Mm-hmm.
So we took care of this. We took care of this convolution. Now the next operation is the 3 by 3, which is a 3 by 3 convolution, and you have 128 filters. So first you do this, then you do that. Then another time you decrease a dimension from 256 to 16 using this one by one convolution. Then you do 32 of 5 by 5 convolutions. And the max pooling is the same. The first max pooling, what is it doing? It is doing it channel-wise. So after the max pooling operation, you're gonna have 256 channels. But then you do a one by one convolution to reduce the dimension to 32. And then in the end, you're concatenating these yellow numbers to get 256. So these are just intermediate operations. Does that answer your question?
Yeah, it does. Thank you.
Any other questions? So this concept of one by one convolutions are really interesting. We are going to see that all over the places. To reduce a dimension, to increase the dimension, and so on. And by dimension, I mean the channel dimension. With convolutional neural networks, the output of every layer and the input to every layer are just tensors. So it means that they are like images. They have 3 dimensions.
This is a more general question. Is there common notation or verbiage for the difference between the dimension you're talking about, like the channel dimension, and the size of the window, like the 28 by 28, or later on 14 by 14? Is that distinguished or meaningful, or is it just
So for notation, you can say this is your X coordinate, this is your Y coordinate, and this is your C coordinate, the number of channels.
Okay.
So each image has a pixel, which is a location in X and Y coordinate. And usually for images, the coordinate starts from upper left corner of your screen. So this starts from here. This is the X coordinate. This is the Y coordinate. And then this pixel here in the screen, that's gonna be, I don't know, the 2nd and 10th pixel. But then at this point, you have 3 numbers. It's a red, green, blue. So that's a vector. Each pixel is a vector. And you have the same structure in your entire convolutional neural network. You're reducing the resolution, but then you're increasing the number of channels. You can think of it as the number of colors that can exist. Okay. Any other questions? And then the rest of the stuff, the rest of a network is, I think, self-explanatory. We are doing 2 of these inceptions and then 2 other inceptions. Max pooling, you know what that is. You know what inception is. You know what max pooling is. You have a couple of other inceptions, and then you have average pooling. This is the global average pooling. In the end, you are going to end up with a 7 by 7 image, and each pixel is going to be these many elements. So it's a vector in 1024. It's a 1024 dimensional vector. Each pixel is that. And then you average them out and you put it here. That's the global average pooling layer. You add a little bit of dropout with 40%, a linear to map from dimension 124 to 1000 because you have 1000 labels. Softmax is going to help you turn these into probabilities. Basically, you want the numbers that are being outputted from your network to add up to 1. That's what softmax does. Once you have the probabilities, you can write down your loss function and optimize the weights. Is everything clear?
Is that linear layer, is that just like a dense, like a fully connected layer to reduce that dimension?
Whenever you see linear, that's just matrix multiplication.
Okay.
You have a matrix that's this dimensional by this dimensional.
So the answer would be yes then, I guess, because that's just what a fully connected, like
Yes,
a dense layer is doing.
exactly.
Okay, cool.
So is GoogLeNet clear? The name is sort of, the paper is written by a bunch of people from Google, and LoNet is a paper written by Jan LeCun. Is one of the first papers introducing convolutions around in 1980, around that time. So convolutions are really old concepts. But the idea of stacking them on top of each other and uh, being able to train them actually is very recent. And they are sort of paying a tribute to that paper. So the people in deep learning are really nice people. So they give each other credit whenever needed. Any other questions?
Looking at this number of parameters per layer as it goes down, and it's strictly increasing, and I know that's partly just a fact or like a property of the number of channels increasing. But is there any rationale behind that? And would it still work? Would we still, or would we lose information if it would say like narrow and bottleneck towards the end?
Convolutions are usually cheap in terms of saving parameters. What is causing us trouble, and these numbers increasing, is the number of channels that are increasing each time.
Yeah.
And let's see what is going to be, where is this number of parameters coming from?
Just the product of the.
It is 7 by 7. So that's the number of parameters dealing with resolution. It's a 7 by 7 filter. Then you have 64. And then you have 3. These were the number of channels that are going inside. Red, green, blue. So multiply 3 by 7 by 7 by 64, and you should be close to this number. So the cool thing about the convolution, that it's independent of the resolution of the input image and the output one. Okay. The number of parameters is independent of the resolution. That's why they are cheap and efficient. But then as you increase the number of your channels, then these are going to be more expensive. So fully connected layers are really expensive. If you look at this one, this is really expensive. And these are just estimates.
Does the stride have anything to do with the parameters estimate?
The stride, no.
Okay.
Stride has nothing to do with that. So yeah, that's a good question. I don't know why this is so off. So 3 by 7 by 7 by 64 is around 9,000. So there is a comment. Seems like the first row is actually a 7 by 1 layer and a 1 by 7 layer. Okay, so it makes sense. So there is a way. I will talk about that in future slides, that you can convert a 7 by 7 convolution and approximate it by a 7 by 1 and a 1 by 7. So yeah, perfect. Thank you, Sorj. And is the ops number just the number of parameters times the number of pixels? These are really expensive operations. See, you need to have a for loop that is gonna take your convolution and slide it over your pixels. So let's say, I think it's gonna be 112 by 112 times that you have to do those multiplications. So you need a for loop on these two. Any other questions? If there are no other questions, let's move on.